discuss now how to generate a simple project by using the Keil microvision tool software. Okay, just select Keil microvision 4, click on setup. Okay, okay, this is the software. These are the different editors. This is called project window, or this is the editor window. Okay, and this is the output window. We are calling it as output window, editor window, and project window. Okay, here we can see what are the list of files and what are the project name and the target we can see here. Okay, and we can write the coding here. Okay, by opening some new text file, anything. Okay, and this is the output window. If there are any errors or warnings, it is displayed here. Okay, now we will start how to do a simple microvision new project. Okay, just project, close project. Okay, no, want you can write the notes also. Okay, just go to project, new microvision project. Okay, now I want to create a new folder at desktop. I want to create a project here. Okay, just create a new folder, just give a name, some demo. Okay, open the folder. Okay, your project name, whatever you want to do, some LED blink. Okay, just save. We need to select our microcontroller. Okay, as our microcontroller is developed by Philips company. Okay, it is based on NXP Philips and the microcontroller name is LPC2148. Okay, just it is in the group of NXP founded by Philips. Okay, just select this one and LPC2148 as we are using the microcontroller. Okay, LPC2148. Okay, just press OK. And it will ask for copy Philips LPC2100 startup code to project files. Okay, we need to select S. Okay, here it will display the our startup code as our this is the project name. Okay, and this is the attached startup file. Okay, now we will see what is there in startup code. Okay, this is the startup file. Okay, here as we have in ARM processor, we have totally 7 modes, that is supervisor mode, system mode, abort mode, fast interrupt mode, normal interrupt mode, and undefined mode. Okay, all the 7 modes are defined with different addresses. Okay, in the startup file. Okay, the main why we are adding startup file. Okay, because of all the 7 modes are added with this corresponding addresses. Okay, and next their stack sizes. What is the stack top size? Okay, all we are including the base addresses. Okay, and this is BPB div. As I told you, some factor we are using for generating our peripheral clock. Okay, BPB divider, Verilog peripheral bus divider. Okay, by generating giving crystal frequency to 12 megahertz, we increase the PLL 0 up to 60 megahertz. But we can use our P clock from 15 megahertz to 16 megahertz by using the BPB divider. By default, our startup file generate a P clock of equal to 60 megahertz. By default, without generating, our startup code will generate a P clock of 60 megahertz. Okay, by taking BPB divider as 0, 1. Okay, this is the BPB div setup, and this is the PLL configuration to multiply our crystal frequency to 60 megahertz. These are the different settings for PLL configurations. Okay, and whenever we start compiling, first our startup file will start compiling. Okay, after the execution of the startup file only, we will enter from startup file to our starting of the main function. That is, whatever you find write as C function, the function will be executed. Okay, that will be here. These are the different execution branch instructions. As I told you, some LDR and STR instructions. These are the instructions. And we are entering from startup file to this is the entering into the C code. Okay, it will store the address of the main function. As we know, generally all C function starts from main only. Okay, so the address of main function will be loaded to some register, that is R0, and that R0 is branch to BX. You know the instruction branch exchange that will jump from current location to R0 address. Okay, the R0 address will be stored into PC. Okay, then the execution will be starts from main function. Okay, this is the importance of the startup file. Okay, just we can say inclusion of the all 7 modes addresses and their stack sizes and PLL configuration and pclock configuration is there, and different addresses are defined in the startup file and entering from startup file to C file. Okay, now I want to write a new project file. I want to write the code for our project. Okay, just go to file, new. This is the new text file created. Okay, this is the new text file created. Just save with a name with extension .c. Okay, just select file, save with a name of .c. Okay, I am saving it as main.c. Okay, this is main.c file which is saved. Okay, now I want to write the code for some LED blinking. Okay, first of all, okay, now I will start the coding of LED blinking, some simple LED blinking. Okay, before writing a LED blinking code, first we need to know how many LEDs we are using. Okay, now I am using 4 LEDs which are connected to our port pins P1.16, P1.17, P1.18, P1.19. Just say, okay, these 4 pins are connected to corresponding LEDs. Now I want to some on or off, do some operations on that LEDs. Okay, so I need to configure GPIO pins. Okay, that means as I am using port 1 pins, I need to configure all these pins as GPIO pins. So I want to use user manual. In the user manual, I can select the pin configuration, the pin functionality selection. We have some registers to select the function of the each pin. Those registers are called pin selection registers. As we have 3 registers, they are in pin connect block. Okay, this is pin cell 0, pin cell 1, pin cell 2. Okay, each all these registers are 32-bit registers. Okay, in the each 32-bit registers, this is P0.0. From port 0, the first pin, that is 0th pin, P0.0, and this pin can be accessed by using first 2 bits, that is LSB, first LSB 2 bits, 0th bit and first bit. Using that, these 2 bits are reserved for port 0.0 pin. Okay, if I want to use this P0.0 pin as GPIO pins, I want to store at 0 and 1 bit with 00 value. Okay, if I want to use as transmitter pin, I want to store it as a 01. Okay, now for our project we are using port 1 pins. Okay, for port 1 pins we are using P1.16, 17, 18, 19. Okay, the port 1 pins will be used by using pin cell 2 registers. Okay, all the port 1 pins can be configured by using pin cell 2 registers. Okay, if I want to use port 1 pins, I need to configure pin cell 2 registers pins as a GPIO pins. So I need to first pin cell 2 as GPIO pins. Okay, just I was starting with first just as in our normal basic C language, we include some header files, stdio.h, conio.h. Same like that also, we are using some include file which includes all the register sets of the microcontroller. Okay, so I am including the microcontroller. Just give a right click. Here # include lpc214x.h. Okay. Okay, this is the header file included. Now I want to start with main. Okay, just write int main. Okay, now I want to configure those pins as GPIO pins. So I am writing pin cell 2, okay, which is equal to all the 32 pins are configured to 000. That means I am configuring all the pins, but we need to configure only P1.16, P1.17, 18, 19 pins as 000 to use as GPIO pins. So I am configuring all the pins because I am not using any other pins. Okay, so the format will be 0x, which indicates hexadecimal formats. okay, and as we are using total 32 bits, all 32 bits are configured by using hexadecimal. Okay, 32 bits we need to write means in the hexadecimal format means all the 32 in the 32 bits 4 bits each nibble indicates. Okay, so I am taking 4 bits as each nibble and writing 8 nibbles here. Okay, they are 1 2 3 4 5 6 7 8, total 8. That means configuring all 32 pins as GPIO pins. Okay, okay, sorry, here I need to say pin cell 2 configures port 1 of 16 pins only. Okay, all these registers, pin cell 0, pin cell 1, pin cell 2, all registers accesses 16 pins of each port. Okay, for example, say pin cell 0 is there. Pin cell 0, we can use pin cell 0 for accessing P0.0 to P0.15. By using pin cell 1, we can access next 16. That means P0.16 to P0.31. By using pin cell 1, we can use P1.16 to P1.31 up to that one. And P1.0 to P1.15 are reserved. Okay, yes, I am configuring here pin cell 2. That means P1 pins as port 1 pins as GPIO pins. Okay, now I need to set all the pins as output or input pins, because I am connecting the pins to corresponding LEDs. That means I am using output function. Okay, so I need to configure these pins as output pins. Okay, to set the output pins we have some GPIO registers. Okay, the registers will be to use those registers we'll go for user manual. Okay, in the user manual we are having GPIO. Okay, this is the GPIO registers, and these are the 4 registers available to access GPIO pins. Okay, that is IO pin, IO set, IO direction, IO clear. Okay, the specification of each pin is IO pin indicates that GPIO port pin value register, which indicates the current state of the GPIO configured port pin. Okay, by using these registers we can read the status of the current port pin, whether current pin is high or low. We can read the status of the current port pin, whatever the status we can read by using IO pin. Okay, next IO set. The IO set register is the output set registers. If you want to configure corresponding LED or corresponding pin as high, we need to give the corresponding bit value to here IO set. Okay, that means these registers controls the state of the output pins in the configuration with the IO clear. That means if you want to on some LED, we need to which pin the LED is connected. For example, say P1.16 is connected to LED. Okay, now I want to configure IO set 1, which indicates port 1, which is equal to the corresponding port pin which is connected to. The bits are reserved now. The bits will be enabled with 1. So when the LED will be on. If you want to on the corresponding LED, okay, we can use IO clear. This is a register used for clearing the register. Okay, to set the corresponding pin as low. This is used for setting the corresponding pin as high. Okay, these are the 4 registers, and this is the direction register, which indicates whether the pins are output or input. The direction of the port pins can be read from using these direction registers. Okay, the explanation about each pin register will be below. Okay, this is port 0 set, port 1 set, and port this is fast GPIOs. This is clearing. Okay, this is some example he has given in the user manual how to use these registers. Okay, now I need to configure all my pins as output pins. So I want to use IO pin, IO direction pin. If I want to use corresponding pin as output, I need to configure control pin as output. Okay, in the corresponding bit location, whatever the pin I am using, that corresponding bit location I need to say with 1. Okay, so in our project I am doing IO direction. As I am using port 1 pins, I need to say IO. Okay, IO direction, because I am using port 1, so 1 IO dir 1, which is equal to, I need to configure P1.16, 17, 18, 19. Okay, IO direction register is a 32-bit register. Now I need to configure 16, 17, 18, 19 pins as ones. Okay. For that one, we have some simple software, tool converter software. This is the tool converter simple software. Okay. Now I need to set 16, 17, 18, 19 pins as ones. So I am using just this is 1, 1, 1, 1. Sorry. Okay. This is 1. Okay. The registers are 000F40. Just copy this value, just paste here. Okay, this is the corresponding value which we are giving the IO direction. That means the pins will be set to output. Okay, now I want to use some simple on and off, LEDs on and off. To on the corresponding LED, that means to set the corresponding pin as I want to use IO set registers. To clear that means to off the LED, I want to use IO clear registers. Now I am using IO set and IO clear. Okay, with some delay. Just first I am taking while one. In the while one, first I am owning the all LEDs. Okay, just use IO set 1 because it indicates port 1. The value will be same, whatever the value we are given in the direction, only those port pins we can control by using these registers. Okay, 0x, okay, this is the controlling of total port pins P1.16, 17, 18, 19 pins. Okay, next IO set 1. This is corresponding pins will be on. Okay, just this is a simple code. Okay, now I want to off the LEDs. Okay, just use the registers IO 0. That is IO same value. I want to off all LEDs, so I am using the same value. Okay. This is some simple code for LED on off. Okay. As we have processor clock is 60 MHz, the execution of each instruction cycle will be 16.66 nanoseconds. Okay, but this is one instruction say, and this is another instructions. Okay, these two are the instructions. One is LED on and another one is LED off. Okay, this is executing in 16.66 nanoseconds, and this one is also executing in 16.66 nanoseconds. But our eye can't see the execution of the simple delay, the very small delay, 16.66 nanoseconds. So I need to include some extra delay by using simple for loops. Okay, just I am saying just delay function. Okay, now I need to define the delay function. I'm using just a simple delay. Okay, because here I am using unsigned int and int. There is a big difference between unsigned int and int. Int difference, that may be signed int or unsigned int. The signed int may be minus 37,000, some value is there. If you use unsigned int, we can use from 64,000. So I am giving some value 60,000. Okay, for some simple delay. Okay, now I want to declare this function. If you define any function above main, we don't use we are not defining any, we don't use any declarations. If you define any function after main, we need to declare that function. Okay, this is a simple delay function, and here also I am using the same delay function. Okay, this is the simple code for LED on and off. Okay, now I want to save this function, save this file, save. This file will be saved, and I want to add the current file to our target. Okay, our project. Just give a right click on source group here. Just add files to group. It will indicate this is the main file we have written. Just select this one and add. Close. This is the main file added to our target. Now I want to compile this file. Okay, whether there are any errors or warnings are there. Okay, just give a right click on source group. Here build target will be there. Okay, it will compile. Compiling, linking, assembling. 0 errors, 1 warning. Okay, the warning will be at last line file end of the. Here in this compiler we bother about only the errors. Okay, whatever be the warnings there, that won't depends upon the compiler. Compiler won't detects the warnings. Okay, we are bothering about only the errors. If errors are 0, the compilation is successful. Okay, just now I want to the compilation and execution of the project will be over. Okay, just I want to generate the hex file. Okay, to generate the hex file we need to do some sort of settings. Okay, just give a right click on target. Here options for target. Okay, these are the different settings we can do in the software. Okay, this is the device, whatever the device we are selected, LPC 2148, and this is the target. Okay, these are the different, and the RAM size, ROM size and RAM size. Okay, and this is the crystal oscillator frequency we are giving 12 megahertz, and we are using non-operating system. If you use RTOS any operating system, we can include the same RTX kernel, all those things. Okay, and this is the ARM mode. Okay, if you want to use thumb mode, we can use. Okay, and this is the output. In the output setting, I need to select create hex file. Okay, and these are the different settings, predefined setting, all these things. If you want further settings, we can change these things. And this is user settings. Okay, all these are settings. Now I want to link up these memory to target, our code memory to target memory. So I want to use memory layout from target dialog. I need to select this one in linker options. Okay, and all the remaining settings are common. Okay, just after selecting the linker and in the linker option, you need to select use memory layout from target dialog, and in the output option we need to select create hex file. Just press OK and rebuild the target again. Build target, creating hex file will be created. Okay, if you want to see the created hex file, okay, my file will be in the desktop. Okay, this is the demo file. Okay, this is our project software, and this is the hex file. This is the hex file created. So we need to dump this hex file to our board, microcontroller board. Okay, okay. Now as board is not present, I am executing in the simulation part only. How we are seeing the all the LEDs, whether registers are setting high or low. Okay, yes. These are the different. Now I need to debug this function. Compilation is over. Now I want to debug this function, whether executing correctly or not. Okay, I want to see in the simulation part only. This is called simulation. If you see the output in the board, that is called emulation. Okay, in the property of ARM architecture, we are concluding some in-circuit emulation. ARM processor in-circuit emulation. That means in the circuit, in the hardware part, we can see the execution, and in the simulation part also we can see. Okay, and to see the output to execute the program, we have some debug part. Okay, just select start debug session. Okay, just press OK. The size limit will be 32 KB because our SRAM size is 32 KB. Flash memory starts from 32 KB to 512 KB. So we need to use minimum size is 32 KB. Okay, just press OK. This is the execution part. As I told you, all the general purpose registers which are present from R0 to R15. Okay, this is R13, 14, 15, SP, LR and PC. Stack pointer, link registers and program counter. And these are the CPS. This is CPSR. NZCV, flags, IV and FT, FIQ, thumb, and these are the different modes. and this is CPSR, and 7 modes: user mode, fast interrupt, interrupt, system modes. Okay, each corresponding mode is having special registers. These registers are called shadow registers. Okay, every mode is having separate special registers. Okay, okay. Now I want to configure these pins. Okay, just I need to whether pin selection is selecting or not. Okay, in the peripherals we have different peripherals, as we have in the microcontrollers different peripherals: UART, GPIO, ADC, timers. All the peripherals we can see in the simulation part also. Okay, just for say GPIO slow interface we are having. This is we are using port 1. So select port 1. This is the port 1 pins. As I told, from port 0.02, port, that is port 1.02, port 1.15 pins are reserved. So in the status pin we can select. This is the pin status, IO pins. That means all these pins are reserved. These pins are we can use. Okay, here only we can conclude. Okay, and these are the different registers as we use in the program. IO direction, this is set for whether the pins are output or enabled for output or input. Okay, if you configure this 0, the pins will be configured for input. If you select 1, the pins will be output. Okay, now I want to execute line by line. We can execute the debugging line by line, or we can execute the total project at a time. Okay, we have different options in the debugging. Okay, just select debug. We have step over. Okay, if you select step F11, that means each instruction by instruction it will execute. If you select step over, the total function will be executed. If you press F5, that is run, the total project will be executed. We have the different options. Now I am selecting with step by step options. Okay, that is for F11 step. Okay, in the functional keys in the keyboard, just press F11 every time. Okay, as I told you, every function starts from, first of all, after compilation in the debug part, it will start from startup file only. Okay, after executing the startup file, it will comes to main function. Okay, just I am pressing F11. Okay, this is the after main only it will come. Okay, by executing the startup file, all the registers will be set. Okay, now initially pincel 2, we can see the pincel 2 register also, whether it is setting to GPIO pins or not. Okay, this is the peripheral, and we are having pin connect block here. Okay, if you select this one, these are the different pins available: port 0.0 and up to port 1.16. Okay, by default all the registers are set to GPIO. Okay, by using these registers we can also set to GPIO, and these are the different registers what are going to be set. Okay, now I am selecting F11. Okay, the pins are configured to pincel 2, that means all zeros, that means P1.16 all are configured to GPIO. Okay, next I want to see these registers whether it is indicating the output or not. Okay, if I press F11, that means 16, 17, 18, 19 pins are configured to outputs. Okay, now F11 just IO set, that means the corresponding LEDs will be, that means the pin will be high. Okay, this is the high, status of high. Okay, with some delay. Okay, delay is completed, then press F11, LEDs will be off. Okay, this is the simple program for LED blinking. Okay, if you press F5, that means if you select debug and if you select run, LEDs will be on off. As the project will be in the while one. Okay, in the embedded we use while one for infinite loop. Okay, as we know, while condition 1 is true for all the times, so we will use while one for infinite loop in the embedded C. Okay, wherever you use while one is for embedded. Okay, infinite loop. Okay, the LEDs will be that the registers will be on and off for infinite loop. Okay, this is the execution of simple LED or using the GPIO pins. How to access GPIO pins? Okay, this is a simple project. Okay.